All right, well, I'm not going to wait 7:30, so to the two of you and the rest. Well, hello again. I'm going to pick up, actually, not exactly where we left off, because we're going to do something quite new. It's time to look at integration. That's the other main pillar of calculus. We had differentiation and integration now, and they both rely on limits. So limit is the foundation, and here is the second pillar. So there's a tool that I'm going to need in order to set this up properly. This first hour is probably going to be more theoretical, and then I'll get onto some more examples. But there's quite a lot of theory to deal with here to set the whole thing up. It's unfortunately more complicated than differentiation, so it takes a little bit longer. But here's a tool that I'm going to need. So I'm going to spend just a few minutes on it. In Chapter 15, Section 15.1 of my book, we'll look at something called sigma notation. And this is a good way to write sums, or at least sums which have patterns to them. So for example, if I have this 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, 1 over 6 squared. Okay, there's a clear pattern to this series. The sum here, basically the main template is that everything looks like 1 over j squared. Actually, I'll use j, fine. 1 over j squared. And if I stick this big Greek letter sigma, which stands for sum, and I put j equals 1 to 6, then this is an abbreviation for this. What this means is you plug into this formula, j equals 1, then j equals 2, then j equals 3, 4, 5, and so on up to 6. And each time you get a term, you get this, and this, and then you stick pluses in between. Now, the point is, it doesn't actually tell you how to find the sum. It's just a notation. It's an abbreviation. But it will come in handy so that we don't have to write out whole lots of things. Suppose I consider this sum now. So it looks like the same as the other sum, except that instead of a 6, I have an n. Well, the point here is that, of course, you sum from 1 up to n. The second last one will be n minus 1 all squared, and the last one will be n squared. So if you just look at this, it looks like j and n are both variables, but as you can see from the right-hand side, there's no j. There's no j. There's only n. So n is the only variable, and it's up here. J is a dummy variable. And we've seen those before, right? In limits, you go limit x goes to 3 of f of x, but x could be anything. So this sum is the same, for example, as k equals 1 to n, 1 over k squared, or say alpha equals 1 to n, 1 over alpha squared. It doesn't really matter. All of these things are just, the alpha, the k, the j are dummy variables, and they can be replaced by any. They're just temporary placeholders. Okay, here's a little trap. What is this sum? Anyone want to take a guess as to what that is? 1,000. Good. It's not 5. It looks like it might be 5. But actually what this means is put m equals 1 and see what that is. Now m becomes 2. See what that is. Now m equals 3. What's 5? It's always 5. So we have 200 copies of 5, and we're going to add them up. So there's 200 copies here of 5, which is, of course, 200 times 5, which is indeed 1,000. Very good. So how about this sum? Sum from n equals 10 to 100 of 1. Any guesses this time? You might think it's 90, but it's actually 91. See, there are 91 numbers between 10 and 100, including 10 and 100. It's a bit of a trick. It's a bit of a trick. In general, if you go from A to B, the answer is B minus A plus 1. So anyway, this is not so significant. One thing that will be quite useful, though, is to be able to write things that in sigma notation that may not be so obvious. So here's an example, and then I'm actually going to move on to integration, or at least setting up integration more specifically. So the example I'd like to look at is, how would you write this sum? Sine 1 plus sine 3 plus sine 5, and so on, up to sine 2999 sine 3001 in sigma notation. I don't ask you to find the sum, I'm just saying how would you write it in sigma notation. Well, let's make a stab at it. We'd like to say maybe sum from 1 to 3001 of sine j. That's not going to work, though, because you get sine 1 plus sine 2 plus sine 3 plus sine 4. So you get all the numbers, not just the odd ones. So how do you get the odd ones? Well, you do 2j plus 1, or 2j minus 1. So I'm going to pick 2j minus 1, and so this is no good. Let's try our second attempt. If you go sine of 2j minus 1, you see, when j equals 1, you plug this in. 2 times 1 minus 1 is 1. But when j equals 2, you get 4 minus 1, which is 3. And when j equals 3, you get 5. So 2j minus 1 gives you 1, 3, 5, 7. So is that the correct sum? The reason it's not the correct sum is not what goes wrong at the beginning, because nothing goes wrong at the beginning. It's what goes wrong at the end. In fact, the last term, if you put in j equals 3001, 2j is 6002. So when you subtract 1, you get 6001. So we've gone too far. We've gone way too far. What you actually need to do is you need to say, where do we stop? Well, the last term, you want sine of 2j minus 1 to equal sine of 3001. So that means 2j minus 1 equals 3001. And if you solve this, you find that j equals 1501. So the correct answer is actually the sum from 1 to 1501 of sine 2j minus 1. That gives you the sum that you're looking for. Now, to be honest, we're not going to be using much sigma notation for the moment. Just to do integration, we need the most. I need to write down one sum, but we don't need to do it a lot. So I'm kind of setting this up for the next half of the course, Math 104 at Princeton, or the second half of the Calculus Lifesaver, where we're going to do infinite series, we're going to do Taylor series, and there we're going to need to do these techniques. So don't worry too much about this now. That will serve as an informal introduction. There's a lot more about sigma notation, telescoping series in section 15.1 if you want to read it up. I'm actually going to skip it because we don't really need it. There will be one particular formula that would be useful if I did a big example in chapter 16, which I'm going to skip anyway. So, no time. Good. So, any questions about sigma notation before I move on? Handy little tool. Excellent. Well, let's move on to integration, whatever that means. Let me try to motivate it by saying that just as I introduced differentiation by looking at how do you work out the speed of an object if you know where it is, and even if the speed is changing. Now my question is, how do you work out the distance or displacement of an object if you know how fast it's going? So for example, if you're looking at your speedometer and you measure it at all the time, every time along your journey you see how fast you were going, how far have you gone. That's the sort of opposite question. So, in order to sort of make this more concrete, I'll give you a few examples of motion between 3 and 5 p.m. So in the first example, I'm going to imagine 3 different cars or 3 journeys that you might have taken. So one example is that you go at 50 between 3 and 5 p.m. Well, of course, you have distance or displacement. I'll assume we're always going in one direction, so they're the same thing for the moment. Distance equals speed times time. And in this case, here's a graph of speed in miles per hour and time in hours. So actually, we want 2 is the time, times 50 is the speed. And what we're looking for is 100 miles. And that's actually the area underneath there. It's a rectangle, height v, and time t, so 50 by 2. Okay, so what if, in fact, instead you went at 40 for the first hour, and then you went immediately up to 60. Now, actually, this is not really possible in practice to get from 40 to 60, as we saw from the mean value theorem. You know, you assume your motion is differentiable. You can't just suddenly accelerate from 40 to 60 in 0 seconds. Let's ignore that little fact for the moment. Maybe you did it so quickly that you can't even see it on the graph. So for the first hour, you went 40. The area of this rectangle is 40. So you went at 40 for 1 hour. Of course, you went 40 miles. Whereas the area of this rectangle is 60, because it's 1 hour by 60. So the total distance is, again, 100 miles. And that's actually the area under this graph. It's not really a curve, but it's the area under the graph down to the x-axis. Okay, so it's quite clear you can make some more complicated journeys. I describe in section 15.2, I'm not going to go into the gory details, but say you, between 3 and 3:15, you go at 20 miles an hour. Well, 3:15, you actually want to mark that as 3.25. 15 minutes is a quarter of an hour. A quarter is 0.25. It's a bit confusing. You kind of want to write 3.15, but that is not quite accurate. So there's your speed for that time. And then perhaps you go at 40 for the next 45 minutes. So there's your speed for that period of time. Then up to 4:30 for half an hour, you might go at, say, 60 miles an hour. And then for the last half hour, you go at 50. Well, again, if you want to work out the distance traveled, you simply work out the area of each rectangle. In a quarter of an hour, you went 20, so that means you went 5 miles in that period. For 3/4 of an hour, you went 40. 3/4 of 40 is 30. Here's a half by 60, which is another 30. Then you go another 20. It's half an hour at 50. It's not 20, it's 25. All right. So here's a nice little construct. Let's try to generalize this situation. Suppose your journey starts at a time A and finishes at a time B, and then let's call, there's some time T1, and there are other times T2, and they could be spaced differently, and we don't know how many of them there are, but eventually they stop. And in order to be consistent, let's let the last time be Tn, which is the same as B, and we'll let the first time also be T0. So what we have, just to reiterate this, is a whole bunch of times beginning with T0, which is just A, and ending with Tn, which is just B. And they're getting bigger. And I want to assume that there are different speeds, not necessarily in increasing order. V1 is the first speed you go at. V2 is the second speed, and that's between t1 and t2. v3, which could be down here, and so on. So v4 would be here, and the last one will be called vn. Of course, there's more of them in here. I don't know how many. I don't want to restrict myself to only 5 or 6. So in this time period, there's v1. That's the speed you're going. And then v2. And then v3. And so on until the last time period, your speed is vn. And my question is, how far have you gone? Well, in this time period, your speed is v1, and the time is t1 minus t0. So here, the distance is v1, t1 minus t0. What about in this second time period? Well, now your speed's v2, and it's taken t2 minus t1. And then, of course, the third period, v3, t3 minus t2, and so on until you get to this last period where your speed is vn, and the time is tn minus 1. And of course, these are the distances of each little part of your journey. And to get the total distance, you add them up. So what we're looking for is the sum of all these quantities. And this is a good reason to use sigma notation. Your total distance, then, is equal to the sum vj tj minus tj minus 1 from j equals 1 to n. And if you check this, you can see it's correct. For example, when j equals 1, you get v1 t1 minus t0. And that's exactly this quantity. When j equals 2, which will be the next one, you get v2 t2 minus t1, which is this. And so on until the last one, vn tn minus tn minus 1. Okay, so this sigma notation wraps up that distance in a very nice way. Okay, so that's a nice little description of how to avoid using calculus altogether, but only worry about journeys where you have constant speeds over certain amounts of time, and then when you change your speed, you magically change it to some other time. Of course, it's not to some other speed, rather, at an instant of time. This is not very realistic, as I said. You kind of got to get faster and slower. So, what I want to talk about is a more general sort of journey with continuous speed. But before I do that, I have one more little wrinkle there. What if you are allowed to go backwards? You're still going along this long highway. I'm not worrying about journeys where you turn right and left and one-dimensional journeys. So my question is, what if you go backwards? Well, remember, this is not really speed. We should think of velocity, where negative means you're going backwards. So we have some idea of forwards and backwards. You can think of it as backing up if you like, or if you want, you can turn around and just go like that. But, I mean, suppose that, for example, you go forward. So let's make the journey between 3 and 6 p.m. now. I'm going to go a little bit longer. Suppose you go in the forward direction at 40 for the first hour, but for the next 2 hours, you go backwards at 30. Well, the graph of velocity versus time should really look like this. So in the first hour, you cover 40 miles going forward, but then you cover 60 miles going backwards. 60 miles, right? It's 2 by 30. And if you try to add up 40 and 60, you get 100. And that tells you actually how far you've gone, but it doesn't tell you where you are, right? If I go forward 40 and then back 60, I want some way of telling that I am actually 20 backwards of where I started. My displacement is 20. So the true idea is that I actually have to think of this as minus 60. That's not the area of this rectangle, because the rectangle is 30 by 2. But it is the signed area, S-I-G-N-E-D. So the idea of signed area is that we're going to count anything below the x-axis as negative. Whatever its area is, you stick a minus sign in front of it, and you will get the signed area. So in this case, the signed area of the whole thing is 40 plus minus 60, which is minus 20. And that is indeed the displacement. You've gone forward 40, and then back 60, and the minus sign helps you with that. Now, on the other hand, if you took the absolute value of this function here, you would get the speed at any one time. So, sure, you're going at 40 for the first hour, from 3 to 4 p.m. And then, as far as you're concerned, without caring that you're going backwards, you take the absolute value of minus 30, it flips it around, and sure enough, you'll get an area of 60. And then the total distance that you've traveled is 100 miles. So this is the displacement. So in other words, and I'll write this down more formally later, to find the displacement, you take the signed area under the velocity curve, right, up to the axis. So either down to the axis from above or up to the axis from below. Whereas to find the distance, you've got to take the absolute value of the velocity curve to find the speed curve. They don't look very curvy. Still call it a curve. All right. So these are important concepts. Any questions from anyone here for the moment? Question? Sure.
How does sigma notation relate to this?
Well, the sigma notation, as I say, I introduced it as a nice tool, but I've already brought it out once. What I've done is I've expressed the distance so far of a journey that is in multiple segments. I'm just considering at the moment journeys where I go at a constant speed for a certain interval, then I change speeds immediately, instantly, and I do that some number of times. This is going to be the distance that I've traveled. I decomposed it as a written out sum with dots in it, but you can wrap it all up into this sigma notation nicely. So it's just a shorthand. It is really just a shorthand. It does make certain computations easier. We're not even going to see those until Math 104, really. So for the moment, it's just let me write out these dots in one little compact notation. Okay? Now, I promised you a more general journey, and a more general journey you shall get. What if your velocity now changes? Here's the beginning of your journey, time A, time B. So here, you start at a certain speed, you get faster, then you decelerate a little bit up till B. If you're going to find the distance, well, it's still going to be this area here. I say distance, speed, distance. I mean, if everything's positive, then distance and displacement are the same thing. Velocity and speed are the same thing. So what's that area? Kind of hard. So here's the idea. Suppose I just focus on a little period between, say, P and Q. And I say, how far did I go between P and Q? Well, look, the speed changed quite a lot between here and here, but maybe in this little time it didn't change very much. And I can say, look, I know I was slowing down a bit, but I was basically going from like 51 down to 50 or something like that. And, I didn't draw a scale on these axes, I didn't give numbers, but my speed, it didn't change very much. And of course, the closer these are together, the less chance your speed has to change, at least if your function is nice and smooth like this. So what the hey, we'll just pick some representative point in between times P and Q, say C, and we'll say, look, our speed at C, whatever that was, we'll just pretend that our speed at C was the same as the speed, between P and Q was the same as our speed at C. So I'm kind of going to just ignore, I'll straighten it out, and I'll say, look, that's not actually what we did, but it's pretty close to what we did. I'll just pretend that at this time we magically became the speed at C, which should, if this is the function v of t, then this is going to be v of c, the velocity at time c. So I'm just going to pretend that at the beginning P, the beginning time, I magically change to my speed at c. I stay that way until the end time q, and then I go about my journey as it was. And that's not going to be too bad, especially if P and Q are close. And it doesn't actually matter really which C you use. You could use any time between P and Q, including time P or time q themselves. That would still give us a reasonable approximation. Now, why do that with just the time interval pq? You don't have to. You can just pick a whole series of little times, boom, 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 and do this sort of straightening out technique and replace the speeds that you were going on that little interval by that sort of sample speed, as it were. And so this is motivating us to take a partition, which is exactly what I've written up here. So maybe we'll just... This object here, without all the superscripts, this is a partition of the interval AB into, as it turns out, n pieces, n strips. So we have taken this interval between A and B, and we've chopped it up into n pieces, which don't have to be the same width. They can be different widths. And so what I'm really doing is I'm approximating my general journey by one of these journeys that I already understand. I'm not saying that's actually what my journey is, but I'm approximating the journey. So we've got to see how this formula changes. And it doesn't change very much. The only difference is we are picking the TJs. We are sort of making them on whatever we want. You know, we start off with this nice, smooth thing. We're just going to pick a lot of them. And we also need to pick these C's in between. So instead of calling them P and Q, I'll call them T0 and T1, say. That's the first thing. So what I'm doing is I'm picking some time in the middle. And instead of calling it C, I'll call it C1. So I'm saying, okay, here's C1. I'm going to pretend my speed was C1 for this time. Okay, what about between T1 and T2? Well, I'll pick some number C2, and I'll pretend that that's the speed. And I do this all the way up to Tn. The last speed I choose is Cn, and so that will be the speed that I'm using. So what are these speeds? This is V of C1. This is V of C2, and so on up to V of Cn. So actually the formula for the distance, approximate distance in this case, is exactly the same as this, except that instead of the Vj's, I have to use V of Cj. So here, the approximate distance is equal to the same sum, j equals 1 to n, the velocity v at time cj times tj minus tj minus 1. It's the same formula as that. Is that visible on the video? Or is the lectern in the way? I can shift the lectern. Okay, we can all see it. Okay. So as I'm erasing this board, let me just say, why do I say it's approximate distance? Because I cheated. We're not going at the same speed in every interval, or at least we're not going at a constant speed in every interval. So all I've done is approximate the situation. However, as you might sort of think, if you take a different partition with more intervals, which are all smaller in time, you get a better approximation. And somehow we've got to do some limit and take lots and lots and lots, more and more and more intervals that are getting smaller and smaller. And we take a limit of that last sum, and that's going to be the actual area. So that's the motivation for what I want to do. So I'm sort of going to move on to chapter 16, which is the real meat of integration. I've skipped the end of 15, but I'm going to come back to it in the context of what I'm going to say here. So instead of dealing with speeds, I'm just going to deal with functions, and then we'll come back and reinterpret it. So here's the situation. I have a function f. So this is a graph of y equals f of x. No more t's and v's. I'm just calling them x and y, and the function's f. And what I'd like to do is find the area between a and b. That's the problem. Find that area. So I take the line x equals a, vertical line, x equals b, and I find the area enclosed by the curve and the x-axis. That is what I like. That's what I'd like to find. Now, I've got to give it a name. What I'm going to do is I'm going to say this area is the integral from a to b of f of x with respect to x, dx. d dx is differentiate with respect to x. Here I'm integrating with respect to x. I would like this to be the area between y equals f of x, the x-axis, and the lines x equals a and x equals b. So there's the notation. This is called the definite integral. There are indefinite integrals, which we'll look at in a little while. Now, there's a couple of things about this. First of all, we talked about displacements and how the curve could go below. So I need to kind of also consider the situation where the curve might look like this. And what I want to say is, if the curve looks like this, you've got to count this area as negative. So there's a positive area, whatever this area is here is taken away. So actually, if there's more beneath the axis, the total area is negative. And instead of area, I'm going to call it signed area, just like I did before. And so I'm going to fill in the word signed area here. So that's a more accurate description. Right? Normally we don't think of area as being negative. If I said, what's this area? You'd say, oh, it's this plus this plus this. But now I'm saying, no, it's this minus this plus this. Okay, so that's why in my definition I put signed area. Now this definition is fine, but it's just about as good as saying, what's dy dx, or what's f prime of x? F prime of x is slope of tangent to y equals f of x at x comma f of x. Okay, you don't need to write that down because you know that. But you see, if I defined this as f, it would not help you calculate it. As f prime, rather. It would not help you calculate it. We need a formula for it, and we saw that the true definition is something like this. It's a limit, and it's a limit of a 0 over 0 type, as it were. The top becomes 0 over 0 if you actually, well, it becomes 0 over 0 if you plug in h equals 0. Now, I want to do a similar thing for this. This is the true definition, and this is the interpretation of the derivative geometrically. All we've got here is the interpretation. What is the true definition? Okay, well, before I state it for you, what I'd like to do is I'd like to give a couple of examples. Switch pages here. I'd like to give a couple of examples, and then I'll give the definition. So, even without knowing the definition, we can still work out some simple things. What is this area? Well, what is this integral, really? Let's say I go from 0 to 1. So this is the integral from 0 to 1 of x dx. What is that integral? Well, we have to understand what it means. According to the definition, you draw the graph of y equals x, which is just a straight line like this, and you go from 0 to 1. Technically, you should draw vertical lines here and here, but there's nothing to worry about at 0. So it's just this signed area here. Well, that's not too hard. We don't need calculus to do this. I'm just looking for an area of a triangle, right angle triangle, with base 1 and height 1. So that's 1/2. Half BH. How about the area, or the integral from 0 to 2 of the same thing? Well, if you go all the way up to 2, you get a bigger triangle. It's a 2 by 2 triangle, but that times a half is 2. Now, there's no units in this. It's the signed area in square units, but you never put units on the integral. So technically, I could have written signed area in square units. I don't want to get too bogged down with units. Don't worry about them unless you are actually solving problems like motion problems where you know what the units are, miles per hour, etc. Okay, so that's all very well and good. How about this integral? Integral from -2 to 5 of 1 dx. Well, in order to set that up, we go from -2 to 5. We draw the curve y equals 1. Not much of a curve again, it's actually a line. The line is still a curve, I guess, although a curve is not necessarily a line. And we have to find this area. This is 7 here. This is 1. So actually, it's a 7 by 1 rectangle. All right. So this is all very nice. Let's see if I can give you another example. What is this integral? Minus pi to pi sine x dx. Looks pretty tricky. Let's draw a graph. Minus pi to pi sine x looks like this. This is y equals sine x. So what I'm asking for is this area. That's what that integral represents. Actually, it's that signed area. What is that signed area? 0. Luckily, this balances out this by symmetry, and this equals 0. A miracle occurs. Just don't ask me for the absolute value of sine x, which would flip this around, because we can't do it yet. We will be able to do it, but we can't do it yet. So actually, this is a special case of this following nice little result. If f is an odd function, then the integral from minus a to a of f of x dx is equal to 0. As long as the function is defined and integrable. There are some nasty functions which are not integrable. We're not going to worry too much about them. But as long as the region has to be balanced from minus a to a, then everything to the right is mirrored by everything to the left, except that the stuff in the left is the opposite way. And so whatever this is, the negative part will be the negative of, and when you add them up, you get 0. It's kind of a nice fact that you don't really even need calculus to at least observe, although we will use calculus to prove it next week. We do substitution. Good. One other little comment before I get on to the actual definition. And here it is. What is this integral? Integral of sine q dq from minus pi to pi. Well, I mean, hey, look, if I just change this axis to the q-axis instead of the x-axis, and look at the definition and say, oh, well, it's the signed area between y equals sine q, the q-axis, and q equals minus pi to pi. Of course, this is the same as this. Who cares what the thing is called? This equals 0 as well. The point is not that it equals 0, but that this is the same thing as this. And the reason is, again, x and q are dummy variables. They get integrated out. They are replaceable as long as you replace them all together. You can't go sine q dx, but you could go sine v dv or sine alpha d alpha. And this is true for any function, in fact. This integral, f of x dx, is also equal to the integral from a to b of f of any other variable you like. Capital V stands for any other variable because it's just a dummy variable. All right, moving quite nicely along. Any questions? If you have one, you know the drill. You can start to shout it out. What I'm erasing, I'm almost going to rewrite, but not in as much detail. Okay. So, I got to define this integral now. I'm going to just take as my inspiration what we did before with the velocities. What I want to do is chop up the x-axis now, and it's no longer a t-axis, or it could be, but I'm going to call it x. I'm going to chop this up into a partition. So I'll take a partition, x0, looks exactly the same as it did before. I'm just letting this be x0, and then x1, x2, x3, and so on up to xn minus 1 and b, which is the same as xn. And then I'm going to pick a representative point. It doesn't matter where. It could just be anywhere between x0 and x1. I will pick some point that is called C1. And I'm going to go up to height f of C1. It's no longer v, it's f of C1 now. I'm going to take that rectangle. And the area of that rectangle is, of course, x1 minus x0 times f of C1. And I'll do the same thing maybe for here. I'll pick this endpoint. So maybe C2 is the same as x2. That's allowed. C2 could be anywhere between x1 and x2. Same with C3, anywhere between x2 and x3. This is the same picture as I drew before, so I'm kind of scratching away at it. So first of all, choose this partition. And actually, you could choose the n even. You can choose how many strips you want. You just choose it, whatever you like. And then you also choose C1 between x0 and x1, i.e. we'll use our interval notation. We'll pick C1 in the interval x0 up to x1. And we're also going to pick C2 in x1 up to x2, even possibly including x1 or x2. And we'll continue to do that until we get Cn in xn minus 1 xn. And so what we've done then is we're going to approximate the heights, as I said, by f of C1, f of C2. And as we saw before, the approximate area is given by, now it's f of x, f of C instead of v, and instead of t, I have x. And this is from j equals 1 to n. And in fact, since the area is the integral, I may as well write it down as this formula here. The integral, which is that actual area, signed area, is approximately equal to the same sum that I just wrote. That is a good approximation, or it could be a good approximation. In fact, you would hope that when n is large, the more strips you take, the better the approximation. Now, I should mention that this is called a Riemann sum, after the great mathematician Euclid. No, Riemann, of course. Now, this is a particularly nice way of approximating an area, but it still doesn't tell us what the actual area is. So, here's the deal. We just take n to be large, and it works. Right? That's all we need to do, take more strips. Well, not quite. Have to be a little careful. Suppose I take many, many little strips. And then I have this one big-ass strip here. And then I take more and more strips, but I keep leaving the big one. That's still going to have quite a big error, right? We're using this area here to approximate this area. And there's this big overhang here. That's no good. So we cannot just let the number of strips get larger and larger. They also have to get thinner and thinner. Right? Even if I took many, many more in here and made this more accurate over here and this more accurate over there, this is still going to be a glaring inaccuracy, and we need to fix that up. So I'm going to let the mesh of the partition, the mesh of our above partition, it's called, is the maximum of the lengths x1 minus x0, that's the width of the first strip, x2 minus x1, which is the width of the second strip, and so on up to the width of the last strip. I take the largest of them and I call it the mesh of the partition. And what I want is that I want the mesh to go very small. I want that to be very small. Of course, if the mesh has got to be no more than, say, this tiny little bit, I may have to take lots and lots of strips. So as the mesh gets smaller and smaller, the number of strips increases. But you can't have this situation, because here the mesh would be this length, and that's too big. We want it to be smaller and smaller. So now, given these definitions that are on this board, I can actually define the integral as an equality as the limit of this as the mesh goes to 0 of the same thing, of the limit of the Riemann sum. And that's sort of the definition of this definite integral. Why do I say sort of? Because this is not a very clean limit here. There's too much choice. What does it actually mean? Well, I don't want to get too bogged down in it, but let me just say that it turns out that if f is a continuous function, if f is nice and continuous, or possibly it is discontinuous at a few different points, but doesn't have any asymptotes. I want it to just be a nice bounded function that might look like this. That's okay. It doesn't matter if it has a few discontinuities in it, as long as it doesn't blow up like this. If it did blow up, it's called an improper integral, and we're going to deal with that in Math 104, a few chapters from now in the book. So if you're watching online, it might seem like a few weeks from now. It's actually going to be next year. You all might not even be here if you're not taking Math 104. So anyway, the point is, it turns out that if f is continuous or almost continuous, but at least bounded and not too discontinuous, then what you do is you take a partition and you choose your CJs. And then you say, oh, I can do better than that. So you take a new partition with a smaller mesh. So you actually just add in some more rectangles here. And you do that and you keep repeating. And each time you can choose exactly what your CJs are, and you can choose where you split it up. And it doesn't matter how you do it. It doesn't matter what your CJs are, and it doesn't matter how you space it out. As long as the mesh goes to 0, for a continuous function or an almost continuous function which is bounded, this turns out to be the same limit. And that is a theorem which we're definitely not going to prove. We're not going to prove it. I want to show you a little bit of a reason why it might be true, but not all of it. Not all of it by any means. So the point is, though, that this does actually make sense, but it is a very complicated limit. And it's a really nasty limit to try to calculate. So we're not really going to try. So I'm going to just move back to the last section in Chapter 15. Just to give you, basically I need to define two types of Riemann sum, an upper sum and a lower sum. And I'll just use those and wave my hands around for about 30 seconds or so as to why they are useful in defining that integral or showing that it exists. So there's two special Riemann sums for a given partition. Suppose you have some function like this, and you start off with a partition Okay? Remember, you're allowed to choose your CJs anywhere in between. Suppose that on each interval, you choose your CJ to maximize the value of the function on that integral. So between here and here, I'm going to choose this point here because this is the maximum. That will lead to this strip. Between here and here, the maximum's in here. Here and here, the maximum's there. Here and here, the maximum looks like here. There, the maximum might be there. Here, here. So that doesn't mean I choose the right endpoint every time. Here I'm choosing the right endpoint. There it's sort of in the middle. There it's the left, 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 right, right. It doesn't matter. I'm just choosing the maximum. And I will get a staircase which is above the curve. And this is called an upper Riemann sum, or just an upper sum. Sum. So Cj is the global maximum for f, but just over the interval xj minus 1 up to xj. And that's true for every one of the partitions, every one of the strips in the partition. So, of course, there's also a lower sum where for the same curve and the same partition, I don't know if I'll be able to draw this thing accurately. Maybe I should have just done it on the same axis. But now you always want the lowest possible value on each one. So we're actually going to look at a problem that involves upper and lower sums in a few minutes, maybe 10 minutes. But for the moment, so this is the lower sum. And again, Cj is minimized as the minimum for f on xj minus 1 xj, and that's true for every j. Okay, so there's your upper sum, there's your lower sum. Now, I said I'd give a little bit of a flavor of one of the reasons why that previous limit works. Actually, whatever CJs you pick, you will get something in between here and here. Right? So the upper sum, for example, for this rectangle would give you this. But if you pick something in the middle, you get this or this or this. So actually, your upper sum is, for any one partition, the upper sum is the biggest it could possibly be. And the lower sum is the smallest it could possibly be. And you can show that if f is continuous, or at least not too badly discontinuous, then the lower sum and the upper sum converge to each other as your mesh goes down to 0. So the upper sum and the lower sum are like sandwich or squeezing the whatever you chose down. So that's why actually you can choose the CJs to be anything. Because no matter what you choose, the area that you get, the approximate area, the Riemann sum, will be in between the upper sum and the lower sum, and they actually converge. So I haven't proved anything, but I've given you an idea of how the proof actually goes and why the CJs are not so important. Yes, a question? Yes. Okay, so the question is, I wrote the domain of one strip as xj minus 1 up to xj. But in this Riemann sum, you see xj minus 1. And you're wondering about the order of it? Well, it's because xj is bigger than xj minus 1. Right? I mean, if I have the interval, say, from 1 to 3, I write 1, 3, but the length of the interval is 3 minus 1. That's why it looks like that. All right. Any other questions? Okay, so guess what? We've got a definition. We've got our upper sums, we've got our lower sums, and we understand everything in terms of signed area. And now, there is an example in the book, in section 16.2, of using the definition to find this integral. This is the sort of non-trivial integral. That integral, you take the curve y equals x squared, you go from 0 to 2, and you take this area here, And that is not something you can do really without calculus. You've got to do some limit like this because the thing is curved. So I don't propose to go over this example in detail because I don't have time. Okay, it's unfortunate because it's a nice example, but it is quite involved. Now maybe I'll do it after the video stops rolling at 9:30 if you want to see it, but I just don't have the time to do it. I've got to cover so much in this class and the next class. So, but I encourage you to read the proof that integral, that area there, mysteriously works out to 8/3. Now, actually, once we do the fundamental theorem, we will be able to prove this. But there's a proof in the book, as I say, of using this definition with the Riemann sums to actually show that that integral is true without using the fundamental theorem. And if you look at that, you will see that it's a real difficult thing. It's not an easy thing to use. So integration using the definition is much, much worse than differentiation using the definition. Remember, though, when we first did derivatives, we did write limit of, as h goes to 0, of f of x plus h minus f of x over h, and we actually worked these out. And then we said, oh, screw that, we've got the chain rule, product rule, and we've got our rules, and oops, there goes my microphone. Still on? Okay, good. And so, yeah, I mean, basically, we're going to come up with similar rules for integration and make this much, much easier. So with your forbearance, I'll skip that. I actually left as an exercise in the book another formula that I'll need, which is that if you only go up to 1, you only get 1/3. So if you go up to 1, that's 1/3, just down here. Okay, so those are formulas that I'll use in a little bit. Excellent. Now, I move on to 16.3. I'm really churning through this stuff pretty fast. What is it now? About an hour. Okay, so moving on to section 16.3. These integrals have some nice properties. And these are properties that you have to know, and they're quite important. So here's the first property. If I integrate from b to a, this is the hardest property, by the way. I'm starting off with the most difficult one. Suppose that b is bigger than a. Well, it turns out that that should be interpreted as the negative of the integral from a to b. What does that mean? Well, think of it this way. If I said, how far did you go between 1 p.m. and 3 p.m.? You'd say, oh, I went 50 miles. Of course, if you've gone backwards, you should say, oh, I went minus 50 miles. Talking of displacements, of course. Now, what if I said, how far did you go between 3 p.m. and 1 p.m.? You go, what the hell? What are you talking about? 3 p.m. and 1 p.m. You mean 1 p.m. and 3 p.m.? No, I mean 3 p.m. and 1 p.m. How far did you go starting at 3 p.m. and going till 1 p.m.? Now, let's assume that you went 50 miles in the forward direction. You would think I was out of my mind, but if I really insisted, you'd have to say, well, if I think of it going backwards in time, like you want me to, from 3 p.m. to 1 p.m., actually I went minus 50 miles, right? Starting where I did at 3 p.m. and going backwards in time, thinking of it like re-rolling the movie. You took a movie of it and you play it in reverse. It looks like I went 50 miles backwards, even though I went forwards. So basically, if you reverse time, then everything goes minus. You look like you're walking backwards. Everything looks backwards. So that's the sort of interpretation of this. I've sort of skipped one little point that doesn't belong in here, but I seem to have missed it. I really meant to say this before, so maybe you can insert this as a footnote somewhere else, that, you know, I talked about velocities and speeds and distances, and I developed this integral, but I never went back and connected the two. Basically, since all the formulas were the same, and we know that the velocity, that the distance rather, or the displacement, is the area under the velocity curve, we now have the following formula, which has nothing to do with this. Displacement is the integral from a to b of v of t dt. It's just the same as what we've been looking at, but instead of f of x dx. I go v of t dt, where we're going, this is the displacement from time t equals a to t equals b, and the assumption is that your velocity is at time t is given by v of t. So you can interpret this two ways. One is it's just as the area, and two, you can think of it as the Riemann sum, a limit of all this little approximating journey where your speed was actually pretended to be constant over tiny little time intervals. And of course the distance, instead of adding up all those displacements, is the integral of the speed, and the speed is the absolute value. So you take that curve of v of t, and anything that's below the t-axis, the horizontal axis, you flip up, just as we did in an example before, and you find that area, and that will give you the distance. So those are useful formulas that you should know. One more comment, actually, before I proceed. If we can look back over here in the definition of the integral. You've got many, many quantities here which are very, very small. Right? This is the width of the strip, xj minus 1. The strips are getting very, very tiny. So I've got many things close to 0, but I'm adding up lots and lots of them. N is going to infinity as the mesh goes to 0. So I effectively have infinity times 0. There are infinite many things of 0. Of course, there aren't actually ever infinitely many, and none of them are actually 0. But in the limit, that's the type of indeterminate form. So just like a derivative is like a 0 of a 0 indeterminate form, this one is the infinity times 0. So it's a little bit different. It's the product form rather than the quotient. Now, the other thing is, because it involves a sum of all these little rectangles, the integral is like a sum. An integral is a sum. It's just a limiting sum of infinitely many small things. And that actually explains the notation of the integral. It is just an S. In the original Newton-type days, they wrote a big S, and somehow the S became stylized as this. So integral is an S, which is a sum. But it's not a sum, it's a sum and a limit. A complicated limit. It's the limiting. It's a limit of a sum. So a derivative is a limit of a fraction, and the integral is a limit of a sum. Anyway, enough philosophy. Integral from b to a is the negative of the integral from a to b. And this will come in quite useful. So for example, this is a silly example, but the integral from 2 to 0 of x squared dx is equal to the negative of the integral from 0 to 2, which, as I just said up there, 8/3, so this is negative 8/3. Okay, big deal. Nevertheless, that's something you've got to know. Okay, property 2. This is for a bit of light relief, but it's kind of useful. What if you integrate from just a to a? Any number a. Well, what does that look like? Here's my function. Here's a. And I want the area from a to a. Well, there's not much of a partition there. Any partition has all the points equal to a. It's kind of pathetic. This has got to be 0. There's no width. So this is 0. Okay, so that's true always. So pick any function you like. Let's take a horrible function like 2 to the power of cotangent x and integrate this from, say, 1 to 1. Well, that's 0. You don't need to know anything about it. Doesn't matter what that integrand is. So actually, that brings me to a couple more definitions, or at least one. As a further aside, I better write this down. I have so much to say, I'm almost tripping over myself in order to say it. As a further aside, I intend to continue some of the other properties, but when you write down an integral like this, it might be worth saying that we need some terminology. This f of x is called the integrand. It's the thing you integrate, the function or the quantity that you're integrating. The dx is not part of the integrand. X is the variable of integration. Almost doesn't need a definition, but you know, sometimes you might have other things in here, other variables that are sort of constant with respect to x, or even functions if you deal with multivariable calculus, and one of them is the special variable you integrate with, so we'll call that the variable of integration. As for the a and b, it's useful to have a name for those as well, and you call them endpoints of integration or limits of integration. And even though this is a really common term, limits of integration, it has nothing to do with regular old limits. Limits of integration is not limits, it's just like the limit, as in the endpoints, it's the extremities of it. So I'm afraid that word limits of integration, do not think limits, just think, oh, just the top and bottom of the integral. Okay? So that's a little bit of terminology. Now, I have to get back to my properties. Here's the most interesting one. If I take the integral from a to b of any function, then I can split it up at c. I can split it up at c. What on earth does that mean? Well, we need a picture. Here's a, here's b. The left-hand side is this area here. Now pick any number c. The first integral just goes from a to c. So it's this shaded area here. The second integral goes from c to b. So it's that shaded integral. All this equation says is, if you add these two smaller areas together, you get the bigger area. Seems pretty straightforward. Of course, it's straightforward. When you look at it in a picture, you need to be able to translate that picture back and forth from the equation and understand that it makes sense. Actually, it even makes sense if c is not between a and b, believe it or not. See, suppose c is to the right of b. What this equation says, there's the left-hand side. The right-hand side says you take this entire integral up to here, and you add on the backwards integral from c down to b. So we're going all the way to there, and then adding on the backwards integral. Of course, by the first property that we did, that integral is going to be negative, and so we're really taking it away. So to get from here to here, you can go all the way to c and then take it away. By the way, the second integral I say is negative. Actually, if the curve is below the axis, it'll be positive. Right? If I go just from b to c here, if I go from b to c, it's negative because it's sine. If I go from c back to b, it becomes positive. So another way of saying that is, if I actually go backwards in forwards time, and then I reverse the time, as in play the movie backwards, it'll look like I'm going forwards after all. So two negatives make a positive. Okay, so this equation is true as long as f is continuous. You know, this obviously doesn't work if the function's not actually defined here, or if it blows up or something like that. Everything has to be nice, all between a and c, or a and b, depending on, or c could be over here. So as long as you don't bust out of the continuity type or bounded type region, then this is all fine. Okay, well, let me give you another example of this. Suppose we want to work out the area from 1 to 2 of x squared dx without using fundamental theorem, just knowing what we know. Well, you can think of this as the area from 1 to 0. Here's one way of doing it. You can split this up at 0, even though 0 is outside the region. So we can go from, instead of 1 all the way up to 2, we go from 1 to 0, and then from 0 to 2. Of course, this looks ugly, but I changed this into minus 0 to 1. And of course, I told you, although I didn't prove it, that this is a third and that this is 8/3. So the answer works out to 7/3. And this is really easy to see again. All I've done is sort of horsed around. I know that this entire area here is 8/3, whereas this little area is only 1/3. So of course this area here is 7/3. All right. Okay, two more properties, both of which are so obvious. They're not really obvious, but they kind of need to be written down. If C is constant, then you can pull it out of the integral. So a constant multiple of a function, the constant is allowed to magically pass through the integral. So the geometrical interpretation, for example, suppose C is 2. Think of this as saying, well, 2f of x is just stretching the function by 2, then the area goes up by a factor of 2. That's all it is. Of course, if you stretched it both directions, it would actually be 4, but this is only a stretch in the y direction. If I have any, take a rubber sheet, something, you know, like a piece of lycra or something, one of those exercise ribbons, draw a little figure, whatever its area is, if you stretch it out by a factor of 2, the area will also be twice as much. Okay, so then the other thing that's just the same as limits and derivatives here. The other thing is well, if f and g are integrable, then the integral of f plus g, if you add up two functions from a to b, then you might as well add up the integrals. This is just like derivatives as well. But of course, this does not work for products. F times g, you cannot just multiply the integrals, no more than you can do the same for derivatives. There you have to use a product rule. For integrals, it's even worse. You have to do something called integration by parts a lot of the time. Not all of the time. Sometimes there's other techniques. But that is right at the beginning of Math 104. I'm not going to worry about it too much. Well, we will see some examples of products when we do substitution next week. All right. So those are the 5 properties that I care about of definite integrals. I told you there's a lot of theory here. I've seen a few examples along the way. Next time, of course, is going to be chock full of examples, but I can't do examples without a little bit of theory, so what are you going to do? Any questions? Well, let me do some specific examples. I'm going to just be bound by the formulas that I already know, which are just those areas of x squared for the moment. Many different integrals will open up to us once we've done the fundamental theorems, which I intend to start in about 20 minutes. But for the meantime, let's look at this question. I propose to consider the curve y equals minus x squared minus 2x plus 3. And I want the unsigned, I want the actual area between this curve, the x-axis, x equals 0, and x equals 2. Consider that problem. Well, we better draw a picture of the situation. This is a quadratic. We care about what happens between 0 and 2 only. At 0, y equals 3. And if I plug in 2, I get minus 4 plus 3, so that's negative 5. And it's a piece of a quadratic, so it must look something like this. And what I'm asking for is, what is this actual area here? I don't even want the signed area. I want the actual area. Well, what if you just take the integral of this function, minus x squared minus 2x plus 3, and you integrate that between 0 and 2, because that's what the question asks. We can actually do this integral. Let's do it. By the properties that I've said, we can bust this up into 3 separate integrals and pull out all the constants. So the 3 integrals are, this is like a minus 1, so we just get the minus the integral from x squared of x squared from 0 to 2. And then we have minus 2 times the integral x squared, of x rather, plus 3 times the integral of 1. If we work this out, we already know this is 8/3, so you get negative 8/3. The integral of x dx, remember this is a triangle, 0 to 2, so it was a 2 square unit triangle. So we don't need calculus for that. And this, of course, is just the constant function 1. So that's a rectangle, 2 by 1. So that integral is also 2. And if you work this out, you get negative 8/3 minus 4 plus 6. That's 2 minus 8/3, which is actually negative 2/3. That cannot be the answer we're really looking for. Cannot be. I'm looking for the actual area that's shaded as if we didn't know anything about signed area, and yet I get a negative answer. What that actual answer is the signed area. So the curve, the graph here is not very accurate because it looks like it's positive. Let me do a better job. What it must look like, it must be more like this. Minus 5 is down here, of course. It must look something more like this. So this area is actually bigger than this area here. I know it's bigger because that's positive, that's negative, and that cancels out this and also leaves some left over there. In fact, 2/3 square units. Okay, so how am I going to find the actual area? Well, the technique is to find this area separately from this area and add up their absolute values. This one will be positive anyway, but this one I've got to change from a negative area to a positive area, and I just take its absolute value. I can't take the absolute value of this, though, because there's some cancellation between here and here that I don't want. So the answer is not going to be 2/3. 2/3 is too small. I need to find this intersection point. And if you think about it, x equals 1. You could factor that, but just look at it. 1 squared minus 2 is minus 3 plus 3. So x equals 1 is the root between there. Okay, the other root is at, what, negative 3? 9, no, it's at, yeah, negative 3. So 1 is, no, it's not negative 3, is it? Yes, it is. Yes, it is. It's negative 3. So the other root doesn't matter, and you have 1 there. So actually, the true area, what I've got to do is I've got to integrate from 0 to 1 of the same thing. And take its absolute value, although we can see that that's going to be positive anyway. And then I integrate from 1 to 2 of the same quantity. And now the absolute value is going to flip that from negative to positive. So let's work out these two integrals. We're going to use the same technique. In fact, I'm going to even do it in place. It's minus the integral from 0 to 1 of x squared, which is 1/3, minus 2 times the integral of that triangle from 0 to 1, which we decided was 1/2, plus 3 times just the integral of 1. So that's that piece. To do this piece, I need the integral from 1 to 2 of x squared, We just did that, and we saw it was 7/3. That was on the previous board. So there'll be a minus in front of it due to this minus. Then I have to subtract 2 times the integral of x. I never actually worked that out, but it's easy enough to do. X looks like that. I've got to go from 1 to 2. So it's this 2-unit triangle here minus this half unit. So that's 3 halves in here. And 3, it's still going to be 3 times the integral from 1 to 2, but it's just a 1-unit square thing here. So actually that's what you get. And if you work this out, the first quantity here is minus 1/3 minus 1 plus 3. So it's 2 minus 1/3, which is 5/3. And the other piece here, I get, these cancel out, and I get minus 7/3. So that's 5/3 plus 7/3, which is 4. So actually this area here, the real area is 4 square units, considering this as positive. And by the way, to check our answer, suppose we didn't take absolute values. I get the 5/3 minus the 7/3, which is the negative 2/3, which we already got above. Of course, it has to be like that. Okay, so the moral of the story is, and this is summarized in 16.4, the moral of the story is that if you want unsigned area, you have to find out where the curve intersects the x-axis and split up the integral into many pieces, as many as there are bits that go above and bits below, basically intercepts. Although I say intercepts, I mean this intercept is clearly not going to cause us any trouble if it doesn't go below the axis. We could go all the way from here to here, nothing will be negative. So I'm concerned only about intercepts where the curve actually crosses and goes through. So you have to split it up into each individual piece. Now, before I move on to something else, what is this integral? The absolute value of x squared minus 2x plus 3. Well, you should be careful when you see absolute values, right? They've always given us trouble. But in this particular case, if you think about what it actually is, if you will allow me to go to this previous picture here, the absolute value is found simply by reflecting the bits below the axis in the x-axis. So the absolute value of this is this curve. This part below got reflected to this thing above. So actually the area we want for the absolute value is this plus this. So that's exactly what we just found. The stuff below gets reflected. So the method that I just taught you for unsigned areas is the same thing as the method for finding the absolute value. Okay, so if you ever have an integral that involves an absolute value, do the same technique. Find where the function is 0 without the absolute value signs, and compute each integral by itself without the absolute value signs, and take the absolute value of each of those pieces and add them up. Sort of counterintuitive that you have to take absolute values of pieces, but that's how it works. All right, if there are any questions, please shout it out. We still don't know how to integrate very much. Just a few little functions, but we understand some geometry now. By the way, in Math 103, this may not apply to other schools, so if you're watching this on video, take it with a grain of salt. But I have to say in Math 103, you really don't have to muck around with Riemann sums too much, at least in terms of final exams. I've not really seen much on the final. Occasionally they'll ask for a definition. Occasionally they'll ask for an approximation using a Riemann sum, which is the next thing I want to talk about. Or actually, there's one more other thing I want to talk about. First, I have one more example. But in a few minutes, I'll talk about estimations. Then I'll start the fundamental theorems of calculus with an aim to finishing them next time. But the point is that the Riemann sum stuff If you don't get it, by all means think about it, but don't get too caught up about it, because there's going to be plenty of more practical examples like this one. Let me show you another practical example. Suppose you have two curves, one on top of the other. And then the two vertical lines at A and B. Of course, the functions can go on after that, but I'm just going to sketch this a little bit. What's this area here? Area between two curves and the lines. Well, this area is equal to the integral of f of x from A to B minus the integral of g of x from A to B. Why? Well, this first integral takes the area under the curve all the way down to the axis. And the second integral takes away this piece. So you get the area between the curves that you're looking for. And another way of writing this, of course, you can combine them, because it's just a difference, into one integral. It's kind of nice. Just take the difference of the functions, and that will give you, and then integrate that. That'll give you the area. But you say, whoa, what if this one is, say, below the axis? Doesn't that screw everything up? What if g is down here? Well, it doesn't really screw it up. If g was down there, then the area between them would be all of this plus this part here. And if you think about it, g would be negative because it's below the axis, and f minus g will be really f plus a positive quantity. So you get a bigger area than you thought, and so it all works out. It also works out if f is also below the axis, or bits of f go down, as long as f is a... So this is the area between y equals f of x, y equals g of x equals a, that vertical line on the left, and x equals b, as long as f is above g. F of x has to be bigger than g of x on the interval. Okay, so if f is on top of g, that's the valid formula. What if f is below g? Well, of course, you do g minus f. So what if sometimes it's above and sometimes below? You take absolute values. In general, this is the area, so I don't know how to say this. This is the area in any case. Even if f and g cross. So for a simple example of this, let's find this area. I'm going to just take two simple curves that I understand, y equals x squared and y equals x. This is a pretty poor diagram. They intersect at 1. I'm going to 2, of course. I want to know what is this area here. What is that actual area, not signed or anything like that? Well, see, between here and here, I need the integral from 0 to 1 of x minus x squared dx. That will give me this integral, which I'll call 1, or I1, let's say, for integral number 1. And that, of course, I split them up. 0 to 1, we decided x has integral 1/2, and x squared has integral 1/3. So that is 1/6. But if I go from 1 to 2, then x squared is on top of x. So I kind of need to take the opposite there. And x squared had integral 7/3 from 1 to 2. We've been reusing the same integrals over and over again. X had integral 3/2. If you take a common denominator, that's 14/6 minus 9/6, so that's 5/6. And the total is 1 square unit. Of course, this is the same. The sum of these two is exactly the same as the integral from 0 to 2 of the absolute value of x minus x squared dx. right? The only issue is when you go from 0 to 1, this is a positive quantity, so you can drop it. When you go from 1 to 2, the absolute value is actually this, because x squared is bigger than x. So I want you to understand that what we've done is nothing other than what we did over there. It's all about absolute values and differences between two things. It's just a little more fancy because we have two functions. But ultimately, we're combining them into one function and taking absolute values in it. So we've done something very similar. Now, in section 16.4.3, I talk about finding areas to the y-axis. I'm going to skip that because I don't have time. But it might be worth reading. I don't think it's going to come up in Math 103, though. If I'm wrong, we'll find out during the reading period. Okay. I still have one more thing to talk about. Almost two, really, before I do fundamental theorems. But that is the way of things. I need to talk about estimating integrals a little bit, because this does come up, and it's an application of Riemann sums. Suppose I have this integral here. E to the minus x squared dx from 0 to 2. I'm going to draw you a little graph of it. It's quite a famous curve. It's called a bell-shaped curve. And it comes up all over the place in probability theory. I'm not going to say much more than that. But this is a really, really important function. In actuality, you put it divided by 2 here, you put a constant out the front. That doesn't matter. There's an asymptote. So if you actually draw it on the graphing calculator, it looks like it hits the axis. But of course, it never does. It just goes down really quickly, exponentially quickly. And I'm going from 0 to 2. Okay. So I'm going to look at a couple of different types of estimates. Turns out, even if you know the fundamental theorem, there's no way to find this area exactly. It just can't be done. In fact, you can prove you can't do it. It's kind of disappointing, considering how important the function is. But it turns out the best you can do is approximate it. So let's try to get a feel for it. This curve has a height of 1. Would you agree that this area is certainly less than this? That's a 2 by 1 rectangle. It has area 2. Right? It's contained within that rectangle. So we know that this is no more than 2. Well, on the other hand, this is the minimum because the curve is decreasing here. And if you think about it, this is e to the minus 4. See, because when x equals 2, e to the minus 2 squared is e to the minus 4. It's 1 over e to the 4. So actually, if you draw, I'll use a different color here. If you draw in this little rectangle, went to mark it, that little rectangle is contained within the big rectangle. Contained not only within the big rectangle, but within the area. Because we've got this lowest point here. And so the area of this rectangle is 2e to the minus 4, because it has height e to the minus 4 and length 2. So actually, that's the most crude sort of estimate we can do. And that's a special example of this principle. If f, any function f, is contained between the lines capital M and little m. So if little m is the minimum of f and capital M is the maximum on the interval a, b, then the integral of f of x dx, that's the actual area, is no more than the area of the big enclosing rectangle, capital M, b minus a, and is no less than the area of this little rectangle. Now, bear in mind, that is height, little m, and width, b minus a. So that's where that formula comes from. That's worth learning. Although, again, it doesn't come up very much. In fact, in Math 103, it comes up a lot in math. I use it all the time myself. It's true. Don't think I don't. Now, here's another useful thing. This is actually a special case of this principle. I'm going to take two curves, and just to be perverse, I know I put f on top. I'm going to put f on the bottom now. Here's f, and here's g. And f is below g, so of course its integral is smaller. So this is also a useful principle. If f of x is always less than or equal to g of x on AB, then the integral of f is less than the integral of g over the same region. And that's a nice property that is also worth remembering. Actually, this is the same as this, but where g is the constant function, capital M, and then also on the lower side where little f becomes m and g becomes f. It's a little bit confusing, but I've just used this principle twice. And I should mention it also works if f is negative, because if f is negative, this is negative, of course it's less than this. It even works if f and g are both negative, because then f would be more negative, and as long as you use signed areas, everything works. With unsigned areas, nothing would work. All these things would go backwards. So this is sort of useful, but I want to look at one variation of this, which I think is a fair game question for Math 103 in particular. And I've seen it occasionally, although I have to say in recent years it hasn't really been emphasized. But I don't know, it seems to me some of the problems in this year's midterm were a little bit different from before. Some of the quiz problems, maybe this will be the year for them to bust this sort of question out. Who knows? I don't actually set these exams here, so I don't even see them until after you take them. So consider this question. I think it's fair game. Estimate the integral from 0 to 2, the same integral that I drew up before, using a Riemann sum with two strips. And actually, I'm going to give you two parts, which I'm going to squish in here. Upper and lower. So A and B. Of course, you could use something in between, but the question is just do an upper sum and a lower sum. Well, in order to set this up, use two strips. It doesn't actually tell me where the two strips are, but if you have any sense, you'll just take the strips to be evenly spaced. So here's my bell-shaped curve, or a part of it. And let's say I take the upper sum first. Okay, you could use the formula, but for such a simple thing, let's just understand what's going on. The upper sum looks like this. And we just need the area of those two rectangles. So upper sum equals, well, what's this height? This is 1, and this is the curve y equals e to the minus x squared. So this is just e to the minus 1, which is 1 over e. And this height is 1 over e to the 4th, as we saw before, e to the minus 4. So actually, the upper sum is just a 1 by 1 rectangle plus a 1 over e by 1 rectangle. Both strips have width 1, so this is the strip and this is the strip. So it's just 1 plus 1 over e. Whereas the lower sum, well, for this rectangle, actually, there's the lower rectangle. For this strip, it's like this. So this is actually a 1 over e by 1 rectangle, and a 1 over e to the 4th by 1. So it's 1 over e plus 1 over e to the 4th. And so we've actually improved the previous estimate from over here. We don't need to linger on it, but just remember what it was. We've improved this to the lower sum is less than the true value of the integral, whatever that is less than the upper sum. Okay, now in Appendix B of the book, of the Calculus Lifesaver, which you guys don't have actually in this room, but hopefully could become available. Appendix B, I talk about different methods of estimating integrals. Use more strips, or you can actually make the tops lines like this, or you can make them parabolas. It's called Simpson's method. The previous is the trapezoidal method. They're not in the Math 103 course, so far as I know. So I won't talk about them. I'm not going to ever talk about them on these videos, I'm afraid, unless I do some extra ones just for yokes. But in any case, they're in Appendix B, and if anyone in the room actually wants to see it, I'd be glad to send you a PDF. You just have to email me. I'll send you Appendix B, but I don't think you're going to need it. Anyway, I still think that problem is fair game. Any questions about it before I move on? Okay, well, I'm supposed to do fundamental theorems, but I have to tell you one more little thing. I have to tell you what average value of a function is, and I have to tell you about the mean value theorem, part 2. I've already done a mean value theorem. Luckily, I can keep this fairly brief. Suppose that you have a fish tank. Okay, so here's a fish tank from the side. And the water, I don't know, you go in there, a little flipper or a paddle or something, and you splash it around so the water's going, woo, and you observe it, you take a photo of the water, and it looks like that. Actually, my father is an oceanographer. He has these long wave tanks, and he studies motions of waves. So he takes a paddle and takes photos, and the water looks something like this at various times. Okay, my question is, when the water settles, how high will it be? It'll be somewhere around here. I don't know. But the main point is that the area, which it's really volume, but we're looking at a cross-section here, the area here has to be the same as the area here. I'm going to call this the average value of f, which I'm going to write as f subscript av. This is, of course, y equals f of x, and I have to understand that this is average over AB. But what I want is that the area of this rectangle, which is the height f average times b minus a, which is the base, should equal the area of the original perturbed fish tank water. And so the definition of the average value is 1 over b minus a integral f of x dx. You're supposed to know this definition by heart. Now I want to explain why this makes a lot of sense to call it the average. Not only does it look like it should be called the average, but you see if you write this in terms of velocities, and you go integral from a to b, v of t dt, and you divide this by b minus a, what do you think this is? We decided that this is the whole distance, or the displacement, the total displacement, and of course the time interval starts at a, goes to b, so the length of time is b minus a. Well, distance over time, or displacement over time, is the average velocity. So actually, this is the formula for average velocity given the instantaneous velocity. The only way you can find the average is to integrate the whole lot to find the total distance, and then divide by the total time. So my definition of f av agrees with what the average velocity should be. Okay, so for example, suppose what is the average value of y equals x squared, or just of x squared, on the interval 0 to 2? You can't just say, oh, I'll plug in 0, I get 0, plug in 4, I get 4, and the average of 0 and 4 is 2. That's not correct. We're trying to average infinitely many values, nor can you plug in every single value, add them all up, and divide by infinity. That doesn't make sense either. So, in fact, the average value is 1 over 2 minus 0, the integral from 0 to 2 of x squared over x squared dx, which is a half times, we've already seen, this is 8/3, so the average value is 4/3. Okay, so then all that's left is for me to state the mean value theorem for integrals. MVT for integrals. If f is continuous, you don't need any differentiation or anything like that. If f is continuous on some interval ab, then f of c equals 1 over b minus a integral f of x dx for some c, at least one c in the interval. So it's sort of like the derivative one in that there's a c, which we don't really know what it is, but we know that f of c is something. Actually, for the derivative, you have f prime of c. Here I have this expression, but of course the right-hand side we already understand. This is the average value. So all this says is that if you draw the average value, the horizontal line, it crosses the curve somewhere if f is continuous. F of c equals f av. I didn't really line these up very well, did I? Now, if it's not continuous, of course, it's not true. The average speed could be, you could jump from 60 down to 40. Say the average speed could be 50. And if it's not continuous and you can jump from 60 to 40, there might be no time you're going at 50. Of course, that isn't true in real life. In real life, to get from 60 down to 40, you have to brake and you have to pass through 50. So this version of the mean value theorem again says, interpreted at least in speeds, that there is some time, c, where your speed, think of this as v, like it is up here, your speed or your velocity is equal to your average velocity. It's exactly what it said for the derivatives version as well. I'm just now interpreting it as integrals. The only difference is when I did it with derivatives, the function f was really your position, and you're differentiating and you're getting the velocity. Here, the function f is really v, the velocity, and you're integrating to get the position. So this is just the other side of the coin, as it were. Two ways of saying the same thing. And actually, the proof of that's pretty straightforward. You kind of just come over here and use this picture, this inequality. You see, you got your m, this is below. You got your capital M, that's above. So if you slide up your line, you've got to use the intermediate value theorem and say, as I slide up the line, this will actually be equal somewhere. And there is a proof in the book. I don't intend to give it. Just in terms of an example of this, the point is we know here that the average value is 4/3. So here is 4, here is 4/3. And there is some value. The c here would be the square root of 4/3, which is, see, because when you square that, you get 4/3. So f of root 4/3, or 2 over root 3, is equal to 4/3, which is the average value. And so that would be the c. There could be multiple c's, but that would be the c, the only one in this example. I think I'm ready to talk about fundamental theorems for 10 minutes. Maybe I'll get to some little bit of it. Anyone have a question? Brief question? Lots of theory. Don't you worry, next time it's almost all examples. Depends how much I can say in 10 minutes. What I'll be able to do is motivate the first fundamental theorem, leave it at that, then probably give us about 15 minutes to talk about the first and second ones, and then next time the rest will be examples. And then that'll be the last regular one for this semester. All right. First, fundamental theorems. What the hey? So in order to motivate this, I have to do something pretty wacky. What I'd like to do is I'd like to find integrals that look like this. Well, as I said, x is just a dummy variable, so let's just change it to t. Just go with this for the moment. Call it a t-axis. What the hey? Of course, I also talked about the integral from 0 to 1. Maybe I want the integral from 0 to 3/2 or something. Why? I don't know where I want it from. Let's just take this and change the top to x. Well, t does not come into this. This is not a function of t. T is just the dummy variable. But this is now a function of x, which I'm going to call capital F of x. So what does it mean? It means that I take this curve y equals t squared, and I integrate it from 0 to wherever x is, and that area will be capital F of x. So I ask you this, what is f of 2? Well, plug in x equals 2, I get the integral from 0 to 2, which is 8/3. I haven't proved it, but we've been using it over and over again. How about f of 1? Well, that was 1/3. What's f of 0? Can anyone tell me? Integral from 0 to 0 of t squared? 0, yeah. If you integrate from a to a, it's always 0, no matter what the function is. So at least we know some of the values of f. But I'd like to know everything about f. I want to know what f is. Because then I could integrate t squared not just from 0 to 1 or 0 to 2, but from 0 to anything. So that's the sort of power that I want. So the way you should think about this is there's some sort of curtain. It's a weird curtain because the rod is not just a horizontal rod, but I can move the curtain back and forth along this weird curtain rod that gets bigger. The bottom of the curtain is always on the floor here. Actually, the curtain rod could conceivably go negative, in which case the curtain inverts, etc., and you end up with negative areas. But the point is that this capital F is a function based on the integral of another function. So it doesn't, of course, have to be t squared. I could take any curtain rod, little f of t. So let's just do this. Let's take any curtain rod, and I don't have to start at 0. Let's just fix a point A, and I want to let the right-hand side be variable. So here are different choices of x, and for each choice I get an area. So based on this function and this point A, I'm going to define a function, capital F of x is the integral from a to x of f of t dt. Okay, so I want you to understand, I started with some function f of t that I want to integrate. I kind of want to integrate just from a to b, but I'm going to fix a and I'm going to let b vary. I'm just going to slide it along just like this curtain here. Okay, again, t is not a real variable. It's a dummy variable, so it's not really a variable at all. A is not, it looks like a variable, but I'm going to hold it constant. X is what I'm going to shift around, the right side of the curtain. And I would like to find f. And here is the amazing result. I don't know much about f, but I do know one thing. If I differentiate it, I get back my original function, not at t, but at x. That's the first fundamental theorem. Next week I'm going to write this up more formally and really explore it. But the point is, in this particular case, let's just see what this means for this case here. According to what I said just now, if this is my function f, then its derivative, capital F prime of x, is just the integrand t squared, but with t replaced by x. So if I define f of x equals this, according to this theorem that I haven't written down formally, its derivative is x squared. Now I ask you this. If you know that a function's derivative is x squared, what is the function? Who can tell me a function whose derivative is x squared? Okay, so yeah, I mean, you might try x cubed because the derivative of x cubed is 3x squared. But of course, then the 3 is out there and you kind of don't want it. So if you do x cubed over 3, or 1/3 x cubed, if you did differentiate this, you would get 3 times a third, which is just 1x squared. Is that the only function whose derivative is x squared? Yeah, what if I add 1 to this? Of course, its derivative is still x squared. I could add 7 or minus 3 or any constant. Are there any others? C can be any constant number here. That's quite a lot of functions. There are infinitely many, one for each c. But are there any others? The answer is no. We proved this about 4 or 5 weeks ago when we did the mean value theorem for derivatives. We showed that all antiderivatives, as in any functions that have the same derivative, have to differ by a constant. So actually, I'm going to call this an antiderivative. After all, what have I done? I have looked for a function whose derivative is x squared. I have reversed the idea of differentiation. These are the antiderivatives. I will probably say antiderivatives or antiderivatives as I feel like it. They mean the same thing. So the antiderivatives of x squared are these. And notice that a function only has one derivative, but it has infinitely many antiderivatives, which all differ by a constant. Anyway, here's the real nub. What's the constant? How do I find c? I mean, I have a few values here. You could substitute any of them if you like. I know f of 0 equals 0, for example, which means that 0 equals a third 0 cubed plus a constant, c. And of course, this means that c equals 0. So c equals 0. And I claim that I've actually found the formula f of x equals a third x cubed. If you believe the first fundamental theorem, that's the formula of f of x. Does that check f of 1 is 1/3, f of 2 is 8/3, because 2 cubed is 8. And hey, we can now find the integral of t squared from 0 to anywhere. It's kind of nice. It's kind of nice. In fact, we don't even have to start at 0. We can go from anywhere to anywhere. Suppose you wanted to start at, say, a and go up to b of t squared dt. Well, remember, you can split this up into the integral from a to 0. We looked at splitting up earlier. And then you can go from 0 to b. And of course, that is really the negative, so I'm going to flip this around from 0 to a and 0 to b. And of course, this is f of b, and this is f of a. So actually, that is a very brief introduction to the second fundamental theorem, which I'm going to quote, but next week I'm going to really do it properly. It says if you want to find a definite integral like this, and actually we can change t back to x because it's just a dummy variable. To find this, find any antiderivative. It doesn't really matter which one, and we'll see why next time. Capital F of x. You don't need a plus c. And then this equals f of b minus f of a. And that is normally written as f of capital X from a to b. So for example, if you want to find the integral from 1 to 2 of x squared, you find an antiderivative, which is x cubed over 3. You could add a constant if you want to, but you don't need to. So you take x cubed over 3, because the derivative of this is x squared. And you evaluate it between 1 and 2. So what that means is you take 2 cubed over 3, so I plug in 2, and you subtract 1 cubed over 3, and you get 8/3 minus 1/3, which is 7/3, which is what we've seen before. Okay, so anyway, that was only 10 minutes. And I just, on fundamental theorems, clearly not enough to really explore it. I just wanted to give you a flavor of it. Next week I'll come back, tighten it up, do a whole bunch of examples on the fundamental theorems, and then we'll look at substitution as well. And that will be it for Math 103. So until next time.